Hello and welcome to part 10 of Dev Maths and Stats course lecture 2. And now finally we come to some example applications of the techniques from today. So there are many applications of differentiation. One of the most common ones is optimization. And optimization we'll look at next week. But another one that's fundamental in social science, economics and other quantitative social sciences is finding marginal quantities. So things like marginal product, marginal cost, marginal utility and so on. So I think I've got 3 examples here. So if you have a factory and the policy of import substitution has sort of been controversial over the years and people argue about whether it works or not. But some countries had problems with it at later stages. But one of the areas which many countries had success with was replacing plastic goods. So instead of importing a lot of cheap plastic buckets, many countries in Asia, Latin America and Africa successfully had their own plastic industries set up. So here we've got an example of a factory producing plastic buckets where the total cost is given by this cubic function. So as I said the other day, cubic functions are often used for total costs, and Q is the total number of buckets and C is the cost in mannats. So the first question is, when the output is 40, in other words when Q is 40, can you use this to tell what's the total cost and what's the marginal cost? So solution. The first part is dead straightforward because all you have to do is put in Q equals 40, so that's how you define the cost function in Maple. Once we've designed the cost function or defined the cost function, just substitute in Q is 40 into here and you can calculate that the total cost would be 22,630 Azeri mannats. I think that's because it's in Azerbaijan, mannat. So that's a simple question. Now, once we know that it costs this much to make 40 buckets, to get the marginal cost, that means when we're making this many buckets, 40, if we make one more, approximately what would that cost to make one more? To do that, we just differentiate the cost function. So you should be able to do this yourself. Maple will do it, so that's the answer. Check you can relate this to this, so that gives you this gives you this gives you this, and this disappears, so that's differentiation. Then you substitute into this, Q is equal to 40. Sorry, Q is equal to 40. And you get 1,765. That's the marginal cost. So the answer is, cost 40 buckets cost this much money, and at this stage to make one more bucket would cost 1,765 mannats. Okay. Any questions? Please ask during the live session. Example 2. A family can work on their own land, or they can hire out their labour time for a fixed wage. This is the classic model of what they used to call peasant economics, where families have got this choice. Should they work on their own land, or should they use that time to go and work for maybe some wealthier neighbours or a plantation or something for a fixed wage? Now, output from their own land is given in kilograms by this production function, Q equals 6L to the half. And we're using that because this has got marginal diminishing returns to labour. So this will be a curve that increases, but the slope will be tailing off like the square root curve that I showed you. So the more time they put into the farm, the more output they get, but the marginal return is diminishing to get less and less time because the land is fixed. And L is the amount of labour time used. The price of the farm output is this, so when they sell it, every 1 kilo they sell brings in 1,000 aries. Alternatively, they can go and work for their neighbours at a fixed rate of 600 aries per hour. So let's define some functions. So this time the Q function like this is the output function. What quantity did you produce if you work on your own farm, where you get 6 times the square root of L. It's the quantity you produce. And what's the cost of that? It's 600 times the labour time that you used. conceptually, of course, this is the first thing you have to realise, is that the cost of working on your own farm is not free, because every hour you put into your farm, you could be earning 600 aries somewhere else. So the cost is 600 per hour working on your own farm. Then you need the revenue function, which is quantity times price. So that's the quantity of crops you produce. So you multiply that by 1,000. This is an awkward way that Maple has of doing that. So it's just this times 1,000. So that's fairly clear. So you have an equation for revenue. That's the amount of money you earn for working L hours. That's the cost of working L hours. Then you differentiate those two, get the marginal revenue and marginal cost. So this is the amount of extra cash you earn if you work an extra hour. This is the cost of working that extra hour. Not surprisingly, it's 600. So you should again be able to differentiate this, and you get this. Then to maximise profit, profit is maximised when marginal revenue equals marginal cost. So you just set this equal to this, 3,000 over L, 3,000 over square root of L is 600, and solve that. So we can multiply by L, and I've multiplied by L first, so square root of L, and then divided by 600, and then squared it to get to 25 is L. So that means the family should allocate 25 hours of their time to working on their own farm. After that, everything should go on wage labour. So in other words, after 25 hours, every extra hour they put into their farm is going to be earning them less than 600 aries, so they're better off working on the neighbour's farm or on a plantation. So that's the optimum point. Okay, and finally, I'm contractually obliged to include some macroeconomics. So here goes. I'm not responsible for the consequences, but here we go. So suppose you have an economy where total planned savings depend on national income, which I suppose that sounds reasonable enough. And total planned investment is a function of the interest rate. So the amount of planned savings in the economy in total depends on, this means that it depends on national income, and the amount that people plan to invest, the private investment, depends on the interest rate. Now, savings and investment in the economy will be equal when national savings equals planned investment. Now, we can use implicit differentiation to differentiate both sides of this equation here. Now, because this is a function in y, this is a function in r, we've got to choose one of these to differentiate with respect to. So I'm going to choose y. So if I differentiate the whole thing with respect to y, so that's ds by dy, I can't differentiate this with respect to y because it is a function of r. So I have to differentiate with respect to r, and then multiplying by this using the chain rule, that converts this into a derivative with respect to y. So I've done the same things on both sides. I'm obeying the golden rule, differentiating both sides with respect to y. So this is implicit differentiation. Now, if you rearrange this, you can find an expression for dr by dy. This thing here is equal to this divided by that. Okay, so far so good. Now we need to think about what's a reasonable assumption for the sign of this, ds y by dy, and this, the ir by dr. In other words, as income increases, what's likely to happen to savings? The answer is that most people assume that as income increases, people save more. So we don't know what this will be, but it very likely be positive. So this is positive. This, as the interest rate increases, the usual assumption is that decreases investment, because if you're having to borrow money to invest, it makes it more expensive to invest, to borrow the money. Even if you've got your own money, you could be earning a rate of R on that money, so it deters you from investing. You'd rather take their return on their money in other forms rather than investing it. So we normally assume that higher interest rates deter investment. So this is negative. So that's positive and that's negative. So if we now do a graph with y on the horizontal axis and r on the vertical axis, what does that tell us about the slope of the graph? So go back to here. If we had a graph oops, like this, that had Y along here and I here. So this is national income, and this is the interest rates. If you wanted to plot some line somewhere showing all the points where this is equal to this, the question is, what would the slope of that line be? What would the slope be? So the slope would be given by dr by dy. Is the slope of a line on this graph here, which is exactly what we've got, dr by dy. And if we're assuming this is positive and this is negative, a positive number divided by a negative number is going to be a negative number. Therefore, we can assume, oops, gosh, what's happening there? Getting excited near the end of the lecture. This is going to be a positive number divided by a negative number, which is a negative, which means it must be sloping downwards. So if you plot some line on here where r equals y, it's going to slope downwards. And normally, of course, it's drawn actually just as a straight line on a famous model which connects income and interest rates are all the points where s is equal to I. We assume that's going to be a downwards line, and we can justify that using this implicit differentiation. So I've got the answer in here. So for dr by y, the top of the fraction is positive, bottom negative, so overall must be negative. The graph of r versus y, of y versus r is the well-known IS curve in the ISLM model of demand. So this line here is known as the IS curve because investment is equal to savings in this model of demand. And this implicit differentiation is one way of arguing that it must be sloping downwards. Now, that's the IS line. Even without knowing this model, you probably realise there must be an LM line as well. So on the exercises, it asks you to try to go through the same kind of reasoning to show which way the LM line should be going. What's the gradient of the LM line using the same technique? So I hope you enjoy macroeconomics, and I look forward to seeing how you get on with that in the problem class. Okay, so that's the end of lecture 2, and thanks very much for watching.